Hello, and my name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we are hosting today's webinar presented by Paragraf, one of our member companies, on the topic of graphene electronics for emerging applications. We're extremely happy to have Dr. Olly Morris from Paragraf, who will be presenting today's webinar. And with that, Olly, I'll give it over to you. Thank you for your time and sharing your expertise today. We're eager to hear what you have to say.
Sure. Well, good afternoon, everyone, and thanks so much, Terence, for the invitation. It's a pleasure to be introducing Paragraf to you all. Paragraf is building a world-leading position in the design and wafer-scale CMOS-compatible manufacture of graphene electronic devices and chips. And this is enabled by a unique and powerful technology, synthesized graphene, on a range of semiconductor and insulator substrates without the need for a transfer process. Furthermore, we achieve this using semiconductor industry standard equipment with processes that are inherently scalable, repeatable, and that yield full wafer coverage. Consequently, our approach dramatically simplifies graphene production, which so far has been possible only by first synthesizing the graphene on a copper substrate, then somehow transferring the graphene onto the insulating or semiconducting substrate needed for the device. This can be an unreliable and costly procedure. Also, and perhaps more importantly, what we do enables the integration of graphene with CMOS. With no transfer process, the opportunity for contaminants to enter, poison, and reduce the quality of the graphene is minimized. And by removing the need to use copper, there is no longer a risk of poisoning other aspects of CMOS production. So the roots of these important advances can be traced back to research undertaken by Professor Sir Colin Humphrey's group around 2014, whilst he was a professor of materials science at University of Cambridge. Sir Colin, who is now our Chief Scientific Officer and a Fellow of both the Royal Society and the Royal Academy of Engineering, is renowned for his expertise, particularly in gallium nitride. And in 2014, he was interested in investigating high-speed electronics, combining both graphene and gallium nitride. For this, he needed a 2-inch wafer of graphene, but finding that no one could supply him with such a thing, he recruited Doctors Simon Thomas and Ivor Guiney, who set about making their own. Their work culminated in the development of novel processes that today underpin our business. And realizing the significance of their invention, Paragraf was formed in 2017. It was soon spun out from the university, moving from the Department of Material Science and Metallurgy to what is now our Cambridge headquarters, a few miles north of the city. On the right, you can see the condition of the facility when we took it over. And in May 2018, seed funding was announced, totaling nearly £3 million, which began to enable a transformation of the site, which has, I think, been quite remarkable. The Series A quickly followed. This was delivered in Q4 2019, and the injection of approximately £20 million has brought the headcount up to 65 people with experience and expertise in a wide variety of material systems, spanning material growth to device physics and manufacture and beyond. The funding has also matured the toolset that we have, which now includes 3 deposition systems, E-beam and thermal evaporation, a photolithography suite, ALD, XPS, RAM and SPM, all housed in ISO 6 Class 1000 labs. And it has enabled the build-out of the facilities required for in-house biosensor development and also the build-out of the commercial team. So now Paragraf are represented both in the US and in Asia. structure of the business has also matured over the course of Series A to focus on three distinct product areas. These are Hall sensors, biosensors, and graphene solid-state devices, and each is advancing along its own timelines to its own business case, and with varying types of and opportunities for collaboration. So our graphene Hall sensors are our most advanced offering, and these are manufactured here in Cambridge at the wafer scale using our CMOS compatible processes. They're shipping now in three types, differentiated by field and temperature of operation. Our GHS-A is optimized for ambient temperature operation and offers 10 times the sensitivity of a silicon equivalent for fields up to 2 Tesla. Our GHS-CM is optimized for fields up to 7 Tesla and temperatures down to 4K. And our GHS-CE is pushing the boundaries of magnetic field measurement, offering measurements up to 30 Tesla at millikelvin temperatures. The sensitivity range of our CM and CE products is presently around 250 volts per amp Tesla. We're working to increase this. All of our sensors benefit from the truly 2D nature of graphene, eliminating the planar Hall effect from the measurement and the measurement of off-axis fields. To date, these products have had a great reception, and we've seen traction in many superconducting applications, including particle physics and MRI, cryogenic applications such as quantum computing, and increasingly in the nuclear industry, where because of the thinness of graphene, it interacts weakly with radiation, making it very radiation tolerant. Furthermore, we can engineer our graphene to provide custom performance, and we do still have some flexibility to work on relatively small volumes. So if you have an application that you think could benefit from a Paragraf graphene Hall sensor, then please do get in touch. Our second most mature offering is our biosensor, and we've now proven this concept here at our labs in Cambridge. The concept harnesses both the biocompatibility of graphene and its electrical sensitivity, and sees the graphene functionalized with a bioreceptor, which a target analyte will bind. This sets the trap, and when the passing analyte, such as a virus or pathogen, does bind to the receptor, this binding in turn modifies the electrical properties of the receptor, so also the receptor-graphene bond and ultimately the graphene, providing a detection signal that is measured as a change in the graphene electrical characteristics. The benefits of graphene in this application include the ability to detect an extremely wide range of biomarkers, because the biocompatibility of graphene enables an extremely wide range of bioreceptors to be used. These biomarkers might be known to us now, or could be waiting to be discovered. Perhaps they might be found in future pandemics. Also, the sensitivity of the material provides a route to measuring extremely small quantities of analyte in a solution. Measurements can be made quickly. For example, a graphene field effect transistor has been used to detect SARS-CoV-2, PCR sensitivity that normally takes around 45 minutes in under 1 minute. And to these benefits, added to these benefits rather, are those conferred by electronic detection, which include no additional reagents are needed, reduced sample preparation, relatively simple multiplexing schemes, highly compact, robust, and portable instrumentation, and reduced variance. For example, sample turbidity has a negligible effect. And when these are compared to other technologies, you can see that graphene, shown here on the right, offers a comprehensive and compelling solution that we believe wins on all fronts in the IVD market, which we have valued at around $70 billion in 2027. This, though, is likely to be a conservative estimate, as it was made prior to the COVID-19 pandemic. So our concept for this sensor is based on a graphene field effect transistor design, and having proven the concept, we are now open to supply chain collaboration around this device, including from those making the constituent ingredients, like the bioreceptors, to end users who want to investigate rapid testing solutions for known and likely future conditions. Okay, and so to our solid state devices category, where we have programs and projects around graphene electronics, and we've begun to take an interest in graphene optoelectronic solutions because we see clear trends in the datacomms market for faster, lower power datacomms links. We believe this lower power operation will favor a continued merging and integration of logic and compute with photonic and transceiver technologies. So graphene components offering more dense packing, circuit simplification, much lower power consumption, faster speeds, and this is the important bit we think, that can be manufactured as part of a CMOS process flow are attractive solutions. And it's great to see that we're not the only ones who believe in this future. Our vision is shared by others, and we note industrial research on this topic, such as NTT's fantastic work towards all optical systems, including graphene-based modulators and switches. Thales's work on optoelectronic mixing to improve and simplify receiver systems, and 2.6 indicating their interest in VCSEL sources that incorporate graphene layers to help spread current and modulate the beam. For Paragraf, in this space, one of the more appealing and compelling applications is the optoelectronic modulator. Here, we believe that device designs do exist that can balance device insertion loss, wavelength range, feature speed requirements, and modulation voltage, where the last of these is constrained such that the modulator can be driven directly from the transceiver logic. Achieving this would be beneficial, we think, because it would reduce power consumption, which is becoming an increasingly important metric in transceiver design. And it will also free up chip real estate, which will enable more dense packing, another important aspect of transceiver design. So on this topic, Paragraf is presently starting to transition theory into practice. This is really exciting for us. Working with a new material, we know that device models can only go so far, will only be believed to a point. So already we're working with others in the community to begin to demonstrate the possibility of graphene optoelectronic devices for datacomms applications and the suitability of our technology for delivering this potential at a scale and a cost that the market demands. We're also working hard to optimize and increase the frequency of our graphene field effect transistors that are presently being developed and deployed into our biosensor program. This is proving to be another very exciting journey for us, with some great results already achieved, and the backdrop to this work is also really exciting. The adoption of all-around gate transistors as a future chip manufacturing node is now quite certain, we think. So now there is a wish to shrink and simplify this concept further. And we note the recently made R&D commitments from some of the world's largest chip manufacturers to support further and future compute roadmaps and manufacturing nodes. For example, right now it's particularly encouraging to see Intel's involving itself in 2D materials, and for this support to come right from the top, with Intel CEO Pat Gelsinger saying recently how Intel won't rest till they've exhausted the periodic table. Today, in this open forum, it's difficult for me to talk more about what Paragraf is achieving in this space, but I do hope we'll be able to say more in public soon. So what does the future look like for Paragraf? Well, we're now closing our Series B fundraising, which has been a very successful and oversubscribed endeavor. And this will fuel our continued growth around 3 product areas of biosensing, magnetic field measurement, and ultra-fast optoelectronics and electronics. And to our Series B plans, we're keen to add others, both to accelerate the development of our product areas and to help advance and support the wider graphene electronics ecosystem and the 2D materials community. Consequently, if you're on this call and are an end user who is interested in exploiting graphene devices to add value to your application, then we'd love to hear from you. Or if you aren't an end user, but have an end user or application in mind and are interested in forming a multi-party collaboration, then please do get in touch. If you're a semiconductor toolmaker, then we would be excited to speak with you about what we see are our future opportunities so that we might work together to develop the tools we will come to need in the future. Tools such as quality assurance to help accelerate the adoption of graphene in volume device manufacture. And if you're interested in joining us, then our worldwide recruitment effort is ramping up to more than double our headcount from device design through product development and production, scientific advisory and oversight boards. Matters relating to biosensing, magnetic field measurement, and high-speed electronics and optoelectronics, please do use the email addresses shown here. And to learn more about the roles that we're recruiting for, do please email inquiries@paragraf.com. So finally, thanks so much for listening today. I look forward to returning with more technical detail in a future presentation.
Olly, thank you very much. Appreciate that presentation. We will send out the slides to everybody so they have that information. This was quite concise, and I like the focus on applications. And it strikes me, of course, that graphene is your enabling technology. That's the secret sauce, and you're really focused on the end use applications. And another part of what strikes me from your presentation is, we talk about sensors, but sensors have so many different types and ranges of applications. So gas sensing, liquid temperature, magnetic, electro control. It's quite a lot of territory to cover. And it's interesting to see it. It seems like Paragraf has a pretty methodical approach to each of those vertical markets and each of those applications. I've got a couple of questions for you, but let's see what the audience has here. If we have a couple of questions from those. I know I saw one comment, which I appreciated. One of the participants had stated, quote, "I've been an electronics professional for the last 6 decades, from the tube technology to the latest developments of ultra miniature, micro miniature silicon chips, and these graphene devices are an eye opener for me." So I think that says a lot, actually, is that this is truly an enabling technology that goes to the next step. And so that brings me to my question for you. Do you guys see that, with this range of sensors that you have, and it really is a range, it's not one or two, but it's quite a broad spectrum. Do you see them primarily as replacing existing technology by being, lower energy, faster, higher sensitivity, smaller format? Or do you really see the opportunity in enabling sensing applications that can't be done with current technology? How would you characterize those two?
Yeah, it's a great question, and I think we're in the fortunate position of not having to choose. So certainly we feel that our Hall sensors will in time be able to displace incumbent silicon devices. The sensitivity of the devices does exceed that of silicon equivalents. And so really that's a cost argument. And as we mature, grow and scale up as a company, I'm sure that we're going to be able to meet those cost arguments. And then there is this other list of things that don't yet exist. And this is really exciting. To be able to provide sensors into things of the future. So a really good example is the fusion community. So fusion has been, it's now being pursued by private industry, where before it was being pursued by sort of nation states. And the size of the magnetic fields that are used in fusion and the other sort of environmental considerations are quite new. Nobody previously people are now looking for sensors that can tolerate extremely large fields at extremely high temperatures, very high radiation environments. And as this technology matures, so the sensing requirements also mature. And something that I haven't included in that presentation is that whilst we've shown rather remarkable performance down into the millikelvin region, the graphene itself is extremely stable. And so we believe it's more a question of packaging to get into these very high temperature operations. And so we are looking at this and we're thinking, hey, can we go on to support the fusion industry who want to be able to more precisely understand and control their magnets to hold their plasma. So it's really exciting. And for us, it's more a question of where are we going to focus resources, because what we don't want to do is run everywhere and do nothing. That's
I think that's a challenge that graphene has faced overall. Because graphene is so versatile, and in your presentation just shows how graphene is this perfect sensing material, and then can be modified. For example, with the biosensors, which of course is another extremely interesting area, that it can be modified. It's the perfect platform, right? And then putting the target markers on there, and then measuring the analyte, which I don't want to get lost and kind of segue from one to the other, but I do have another question about the biosensing.
Yeah,
and it almost seems to me that you can't have enough sensing, and when we start to talk about things like public health, and the recent pandemic is a perfect example. If we had a better early warning system, if you can pick up these viruses and these pathogens much earlier in the transmission sequence, so you can get better isolation, early warning system. So there's so many different ways that we could do a pervasive public health monitoring if we had enough sensitivity in the sensors and targeting at a low enough cost, low enough energy, et cetera. Talk to me a little bit about, where do you guys see for the healthcare and the medical applications? What are some of the most promising application cases you see coming down the pike?
Yeah, so on that, obviously right now the COVID-19 pandemic is concentrating minds, and I think it's concentrating minds where you see governments pushing arguments about sort of mandatory vaccination. And I think people are going to be looking for alternatives to mandatory vaccination, including, more, enhanced testing to catch things, before it gets to that point. So I think that there is really good scope for, let's say, sort of generic platform technologies that can be quickly tailored to emergency situations. And I'm sure that we will deal with this pandemic, and we'll move on from it. But that doesn't mean that it falls off the risk register. This kind of thing is probably going to stay on the risk register for a while, at least in one way or another.
Well, what's been shocking? Sorry to interrupt you, Olly, but what's been shocking to me is the speed with which these pathogens spread around the world. Even when at this point, 2 years in, we have high sensitivity to this. Everybody's on alert. We take mitigation efforts, and yet when a new variant emerges, it goes around the planet in a matter of days. Which scares me a bit, because of course we're all focused on this. It just tells us how many pathogens have been passing around every day for the
Mm.
past, decades with international travel and
Yeah.
such, right? It's just because
Yeah.
we're focused on this one and measuring it that we realize just how much we share.
Yeah. Exactly. And if you go and speak to the you remember what their name is, something like the Cambridge Centre for Existential Risk that has been set up, which is looking at these pandemics, amongst other things. Listen to what they're saying and how this future, what's quite scary is what we've had now. This could be an intentional event in the future.
Right.
And so the likelihood of it happening again, I think, as previously, it's we're not going to deal with this, and then it falls off the risk register. So I think the world would do well to pay a little bit in sort of insurance money and
Yes.
and develop these sort of generic platform testing technologies. So
Absolutely. Yeah. I agree with you 100%. I know we're kind of pressed for time today, so I want to make sure we get in some of these other questions. There's some more of a little more technical. So you've mentioned some of the temperature ranges for operating, and I think what you've alluded to was graphene is not the limiting factor. It's some of the other materials or the device around the graphene that kind of limits the temperatures. But we have a couple. So one of the questions, let me just see here. Can you say more about the carrier mobility that you achieve and the maximum temperature in your CMOS compatible deposition process?
Yeah, okay. So I think the most interesting thing to say in response to that is that our mobility is something we can engineer. In this presentation, I say graphene like it's one thing, right? And actually, there are, for want of a better explanation, as we all know, there are lots of different kinds of graphene. You can engineer this material to have certain properties. And so really where we're coming from is to say different applications will need different abilities. And I think and so I would be more interested in understanding what the application is, rather than just give sort of a maximum value out. So happy to take questions in private, where we can discuss this space more, in more detail.
So let me translate, I think, what you're saying, and this is consistent with other applications of graphene, because you have a high degree of tunability, right? You can customize the material for the particular application, and it's not. I don't think you're saying it explicitly, but I think we've observed this with other aspects. The detailed morphology of the graphene that is produced has a tremendous difference in how it behaves, right? So lateral size and level of defects, and whether it's doped or functionalized or not, et cetera. And so I think you're right. You start with the application intent and what you want to achieve, and then you can work backwards to say what is the form of graphene that will enable that. Is that a fair statement?
Yeah, it is. What we don't want to do is we don't want to work really hard, design a Ferrari for someone that wants to drive to the shops, right? That's
well, unless you want to get there quickly, yes.
Yeah. Yeah, but equally, if you want to go to the moon, we don't want. I'm trying to think of a cartoon example that won't offend anybody.
Well, you can't use a slingshot to get to the moon. You need a rocket ship.
Yeah.
Just a couple more questions. I do want to try to get in while we have you on the line. One of the questions is it possible to replicate all the types of devices that have currently been produced either using silicon or gallium or other group 3 and 5 combinations, including MMICs? Does that question make sense?
I think so. I'll try and answer it, and then if the answer isn't sufficient, I'm sorry, I can't see who asked that, but I'm sure that they'll let me know through a private email. So yeah, we can do a lot to replicate various devices. Some are replicated more successfully than others because graphene obviously is a different material. It has different properties. So, the band gap of silicon is an obvious place to start versus graphene. So, again, I think this speaks to two markets, right? There's do we just want to replicate silicon devices and sort of offer evolution? Or do we want to offer, be very un-British and say revolution? Right? And for us, as a company making its way in the world, whilst I have said that the Hall sensor is very important to us, and there is the opportunity to displace silicon with that, certainly we are at least as excited, if not more excited, about the healthcare revolution that we hope that we can facilitate, amongst other things. So, yeah, I hope that's, maybe I've meandered a little. Apologies if I have, but that's my answer right now. And yeah, to whoever asked that, do send me a message and we'll talk more.
So Olly, there are a number of other questions. People are asking for some specific performance metrics and such. And I don't think we want to address those just yet. I think what I would encourage those who are asking the questions about, mobility rates and how do we compare from transferred CVD, I think those kind of questions, I would encourage them to reach out to you directly, I think, if that's okay. I have, sorry, Olly. And then I have a closing question I would like to ask you. It's more about the business case. We've seen consistently that graphene offers not just incremental change, as you've alluded to, but it's really step change, right? It's orders of magnitude better sensitivity, lower power, tunability applications that you just can't do with legacy materials. What has been the largest barrier? I mean, it's not if this works, we know it works, right? So that's no longer a question. So knowing that you can achieve these step change improvements with all of the benefits that come with it, what's keeping more people from adopting? What is the biggest obstacle to commercial adoption that you have observed so far?
Sure. So, I think it's, from our point of view, it has probably been that graphene has suffered from being overhyped. And the conversation has focused, like we've seen today, it's focused on the mobility, it's focused on the material performance. And whilst that's important, if you want to make your way in the world, the manufacturing integration is that's the real conversation. And the manufacturing integration is, hands are quite often waved at that point. It'll be fine. We'll work it out. And actually, that answer isn't often good enough. It's not been good enough. And so you need to have a real understanding of how you're going to insert this technology into a really well-established fab industry that does really care about scale and cost and quality. if you look at the uptime or downtime, depending on, I guess, if you're an optimist or a pessimist, if you look at the uptime or downtime on the industry, and you look at what you need to do in terms of yield and uptime and downtime to make sure that you're not making them compromise. They don't want to compromise. The industry doesn't want to compromise. It doesn't want to say, okay, I'll take this, but pay a penalty on that. It wants to go, no, I want everything I've got now and a bit more. And so I think that's been the biggest barrier. With graphene, we've been asking people to compromise. We've been saying you can have all this, but here's the penalty. And I hope that as more resources put into this, both at Paragraf and across the ecosystem. The ecosystem is so important. We're so privileged to be a part of it, that we can begin to address these questions of yield, scale, cost, and manufacturing integration.
I can only echo what you've said. I think that from our observation, these other technical issues, but they're not specific to the graphene material itself, right? They're everything that goes around it. Is the reproducibility, the scalability, the cost, integration into existing systems. These are all critical factors. And I think you're right that there's a resistance, especially if you think of the embedded capital cost that most of the customers have put, right? So there needs to be a pretty big incentive for them to switch production processes.
Yeah. And a lot of people, offering this technology, both past and present, very excited about TRL levels, less excited about MRL levels. So I think it's the MRL level conversation that we're addressing.
Well, it would appear so. You've got the tremendous ramp up and you have all the issues that go with, building a company, but it sounds like you have a really substantial team and we'll have a much larger one this time next year. So we're excited for you as well. We're very glad to have Paragraf as a member in the Graphene Council. I want to thank everybody who've joined today to listen and learn something new about this. I think it's really, really interesting, and it's clear that Paragraf should be a good partner for anybody looking to develop next generation devices, sensing devices for a wide range of applications. Olly, thank you for your time.
You're welcome.
And appreciate you sharing your expertise with us.
Thanks so much.
My pleasure. With that, we're going to sign off. So thank you everyone. Have a great rest of your week and enjoy the holidays as they get here.